In the vast, silent darkness of space, 13.5 billion years ago, something impossible happened. In the absolute infancy of the universe, when there should have been only the cooling embers from the Big Bang and the faint, formless whisper of hydrogen gas coalescing in the void, titans were born. Galaxies, as massive and intricate, as chemically mature and brilliantly structured as our own Milky Way, blazed to life in an era that should have been their primordial nursery. This shouldn't be possible. According to the grand, painstakingly constructed edifice of modern cosmology, the elegant story of cosmic evolution, we have told ourselves for half a century, these galactic giants are phantoms. They are apparitions from a future that had not yet arrived, billions of years ahead of their time. The James Webb Space Telescope, humanity's golden eye on the cosmos, was not just designed to see the distant past. It was designed to confirm our elegant story of creation. Instead, what it has found is nothing short of shocking. It is revealing a cosmic history that is far stranger, more violent, more accelerated, and more profoundly mysterious than we ever dared to imagine. Are you prepared to question everything you thought you knew about the universe? The photons being gathered by Webb, these ancient messengers from the dawn of time, are not just refining our theories, they are shattering them. The evidence now overwhelmingly suggests our most fundamental laws may be flawed, that our entire understanding of reality is incomplete, perhaps even naive. We invite you to join the Stellify science community as we embark on a journey to the very edge of time, a journey through the groundbreaking and frankly terrifying discoveries from the James Webb Space Telescope. Together, we will explore a universe that is not only more complex than we knew, but more mysterious than we could have ever conceived. This is not a story of scientific triumph, not yet. This is a story of a crisis, a beautiful, terrifying crisis at the very foundations of our knowledge. The James Webb Space Telescope is, in its purest essence, a time machine. Its magnificent, honeycombed array of 18 gold-plated beryllium mirrors, working in perfect concert, cooled to a mere handful of degrees above absolute zero to suppress its own heat, is not looking out so much as it is looking back, floating silently at the second Lagrange point, a gravitationally stable location 1,000,000 miles from Earth. It is a lonely emissary to the beginning of time. Looking deeper into the cosmos means looking further back into the past, intercepting ancient light that has traveled for billions upon billions of years across an ever-expanding universe to finally grace its sensitive detectors. Every single photon it captures is a messenger from a bygone epoch, a fossil carrying the indelible imprint of the universe's earliest moments. Astronomers, with decades of anticipation and planning, aimed this incredible machine at the furthest, darkest reaches of space-time, expecting to find the universe's baby pictures. They were searching for what they called the cosmic dawn, the end of the cosmic dark ages, that period after the Big Bang's initial flash faded, when the universe was a vast, unlit expanse of cooling gas. They expected to find the faint, small, disorganized clumps of matter and the first fledgling stars, the cosmic seeds from which everything we know would eventually and slowly grow. They were searching for cosmic babies. Instead, they discovered fully grown galactic giants, already aged and mature beyond any rational explanation. A galaxy designated JWST Z14-0 blazes across Webb's sensors like a cosmic lighthouse, its beacon cutting through the fog of primordial time with an impossible, defiant clarity. This single, distant point of light carries a message from when our universe was just 300 million years old. To truly grasp the temporal shock of this, you must understand the scale. If the universe's entire 13.8 billion year history were compressed into a single calendar year, with the Big Bang occurring at the very first second of January 1st, then on this cosmic calendar, our own solar system would not form until early September. Human history would begin in the final few seconds of December 31st. On that same scale, this galaxy appeared, fully formed and blazing with the light of millions of stars, on January 22nd. This is no cosmic infant. It is a developed adolescent. It contains millions of stars that somehow manage to form, burn through their entire violent lives, and die in catastrophic supernova explosions, all fast enough to create and scatter heavy, complex elements like oxygen across its breadth. The chemical readings from its light, parsed with exquisite precision by Webb's near-infrared spectrograph, or NIRSpec, show concentrations of these elements that our models insist, unequivocally, should have taken billions of years to develop. George Reiki, a senior astronomer at the University of Arizona, a veteran in a field not given to hyperbole, calls the finding genuinely mind-boggling. The data implies, with very little room for interpretive error, that this galaxy must have ignited its first stars almost immediately after the Big Bang's afterglow faded into darkness. There was no warm-up period, no gradual, patient buildup of matter. The moment the cosmic dark ages ended, the lights came on everywhere, and with an intensity that flatly defies our physics. This single, paradigm-shattering discovery required over 200 hours of the world's most advanced and expensive telescope's time, focused with unwavering precision on a patch of sky smaller than a grain of sand held at arm's length. Each particle of light captured by Webb's mirrors traveled for 13.4 billion years to reach us. A journey across the entirety of cosmic history, carrying information from a time when the universe was barely 2% of its current age. Webb's extraordinary power comes from its specialization in infrared light. This allows it to pierce through the dense cosmic dust clouds that would have rendered such an observation impossible for other telescopes, like the venerable Hubble. More importantly, it allows it to see the most ancient objects through the phenomenon of cosmological redshift. As the universe expands, it stretches the very fabric of space itself, and any light traveling through that space gets stretched along with it, like a wave drawn on the surface of an inflating balloon. Light from the most distant objects, which likely started its journey as bright blue or ultraviolet light, has been stretched so profoundly by this cosmic expansion that by the time it reaches our solar system, it has become the long, gentle waves of infrared light. The amount of this stretching, the degree of redshift, allows astronomers to calculate a distant object's distance and age with startling precision. But what makes the discovery of JWST Z14-0 so profoundly disturbing is the timeline problem it creates. Our current, gold standard models of physics predict that galaxy formation must follow a careful, methodical, and above all, very slow sequence. It begins with the invisible, the underlying scaffolding of the cosmos, a mysterious, non-luminous substance we have dubbed dark matter, must first begin to clump together under the relentless, patient pull of gravity. Only after these vast, invisible halos of dark matter have formed can normal matter, the hydrogen and helium gas that will become the stars and planets we know, begin to fall into these deep gravitational wells. Within these dark matter halos, vast clouds of this primordial gas must slowly cool, a particularly difficult process in the early universe, which lacked the heavy elements that act as efficient coolants today. Then they must condense, and eventually collapse under their own immense weight to ignite the very first generation of stars. Crucially, those first stars, thought to be gargantuan monsters of pure hydrogen and helium, hundreds of times the mass of our Sun, must live out their entire, furiously short lives, forge heavier elements in their nuclear cores, and then explode as magnificent supernovae. Only then can they scatter those newly minted heavy elements across space, enriching the surrounding gas so that a second generation of stars can form from that more complex, elementally diverse material. According to every computer simulation ever run, meticulously programmed with our best understanding of gravity, thermodynamics, and nuclear physics, this delicate, multi-stage hierarchical process should take, at a minimum, 1 billion years. Yet here, in the ancient light of JWST Z14-0, stands irrefutable proof that a massive, chemically mature galaxy achieved this entire evolutionary journey in less than a third of that time. The universe, it seems, somehow skipped several critical chapters of its own rulebook. And this was just the beginning. This was not an anomaly. It was the opening salvo in a sustained assault on our understanding of the cosmos. Soon after, Webb found 6 more galaxies hovering in its deep field of view, like cosmic criminals caught red-handed. Astronomers have informally, but aptly, nicknamed them universe breakers because they so flagrantly and fundamentally violate the laws we've established for galactic formation. Each one of them measures more than 10 billion times as massive as our Sun, yet they all existed when the universe was a mere 500 million years old. Mike Boylan-Colchin from the University of Texas, a leading cosmologist who now studies these galactic rebels, states with a mixture of raw excitement and deep scientific concern that according to every cosmological model his field has ever created, these objects simply cannot and should not exist. The standard model of cosmology, called Lambda CDM, which has been the brilliant and successful bedrock of our understanding for decades, is now directly threatened by these 6 galaxies, which risk toppling a half-century of established science. The mass measurements confirmed by multiple instruments and independent analytical techniques seem impossible to dispute. Spectroscopic analysis, which breaks down the starlight into its constituent colors to reveal chemical composition and mass, shows that each of these galaxies contains stellar populations equivalent to 100 billion stars. For crucial context, our own Milky Way galaxy, our vast and beautiful home, needed 13 billion years of patient mergers and steady continuous growth to accumulate its 60 billion stellar masses. The burning question that is keeping cosmologists awake at night, scribbling on whiteboards and running new simulations is, how did these ancient galaxies manage to achieve nearly double that mass in 1/20th of the time? Our most sophisticated supercomputer simulations have consistently shown that the conditions of the early universe, hotter, denser, and smoother than it is today, should have actively prevented such rapid galaxy formation. Dark matter halos, the invisible cradles of galaxies, required hundreds of millions of years just to grow massive enough to gravitationally capture significant amounts of normal matter. The gas clouds themselves, lacking the heavy elements that help them cool efficiently today, needed additional, precious time to radiate away their heat and collapse into star-forming regions. Yet, these universe breakers appear to have ignored every single one of these physical constraints. They somehow converted nearly 100% of their available gas into stars with an almost magical, impossible efficiency. Modern galaxies, by stark comparison, are incredibly inefficient, typically managing only a meager 10% conversion rate over their entire lifetimes. The rest of the gas is blown out by supernovae or remains too hot to form stars. Such perfect, instantaneous conversion of gas into stars pushes against the absolute theoretical limits of stellar and galactic physics. Joel Leja, an astrophysicist at Penn State, describes the revelation not as a minor adjustment, but as upending settled science. The research team has been informally calling these objects universe breakers, and they continue to live up to their name with every new piece of data that comes in. Each new measurement only confirms their impossible existence. This shocking discovery originated from the Cosmic Evolution Early Release Science Survey, a multi-institution project that examined a region of space so infinitesimally small, it is roughly equivalent to viewing the full moon through the narrow aperture of a drinking straw. Within this tiny, random, and presumably representative sample of the early cosmos, 6 impossibly massive galaxies appeared where none should exist. This raises a terrifying statistical question that echoes through the halls of astronomy departments worldwide. If such impossibly rare objects appear so readily in every small patch of the early universe we examine, how many more universe breakers are lurking beyond our current detection limits? The total number could reach into the millions across the entire observable cosmos, meaning our entire census of the early universe is wrong by orders of magnitude. This profound cosmic crisis presents 3 possible and equally revolutionary explanations. The first is that our understanding of how dark matter behaves and evolves on cosmic scales is completely and totally wrong. Perhaps it is not as cold or slow-moving as we thought, allowing it to clump together much faster. The second is that some unknown, exotic form of physics, perhaps a new force of nature entirely, governed the processes of star formation in the extreme, high-pressure environment of the early universe. The third, and perhaps most unsettling, is that the fundamental expansion rate of space itself was dramatically different in the past from our current predictions, altering the cosmic clock itself. Each of these possibilities demands that we tear out major portions of our cosmology textbooks and start again from first principles. The universe breakers are forcing scientists to confront the deeply uncomfortable reality that our cherished, elegant cosmic models may be fundamentally and catastrophically flawed. As Webb continued its silent, patient vigil, staring into the abyss for longer and longer periods, even more puzzling and bizarre objects began to emerge from the darkness. Thousands of tiny crimson objects now pepper the telescope's deepest images, like scattered drops of blood on the black canvas of space-time. Astronomers have given them the deceptively simple name Little Red Dots, a nickname that barely captures their profound and deepening mystery. These miniature objects, whatever they are, appeared less than 1.5 billion years after the Big Bang, glowing with an inexplicable, ferocious brightness that defies easy classification. Dale Kagevsky from Colby College, an expert in early galaxy formation, admits that scientists feel utterly confounded by this new and unexpected population of objects. The little red dots challenge every single assumption we hold about early galaxy evolution. They measure far smaller than even the most compact typical galaxies, yet they manage to outshine objects 10 times their size. Their sheer, intense luminosity suggests that something extraordinary, something truly monstrous, is powering their cores. Each little red dot spans roughly 1,000 light-years across, making them incredibly dense and compact by galactic standards. Our own Milky Way, for comparison, stretches a leisurely 100,000 light-years from edge to edge. Despite their diminutive size, these objects are emitting more light than entire galaxies containing billions upon billions of stars. The distinctly red coloration provides the crucial clues about their nature. Webb's powerful infrared observations reveal specific wavelengths, that are the characteristic signature of hydrogen gas being whipped into a frenzy, moving at tremendous speeds. This is the unmistakable sign of material swirling around a supermassive black hole at velocities approaching a staggering 10% of the speed of light. This black hole hypothesis, however, creates its own set of intractable, timeline-shattering problems. Supermassive black holes are not supposed to be born. They are built piece by piece over cosmic eons. They are thought to begin as relatively small seeds, left over from the collapse of the first generation of massive stars, weighing perhaps a few dozen times the mass of our Sun. From there, they must gradually and painstakingly accumulate matter, devouring nearby gas clouds, unfortunate stars, and merging with other black holes. This process is governed by predictable patterns we have observed throughout the modern universe. But the little red dots seem to host fully mature black holes, weighing millions or even billions of times more than our Sun. These cosmic monsters somehow achieved their enormous masses when the universe was still a veritable infant. Our current theories of black hole growth cannot, under any circumstances, explain how they grew so large, so incredibly quickly in the early cosmos. Recent, detailed spectroscopic analysis has confirmed that many of these little red dots do indeed contain actively feeding, ravenous black holes. The gas surrounding these objects shows clear signs of extreme heating and acceleration. Temperatures reach millions of degrees as matter spirals inexorably toward the event horizon, the point of no return. This feeding process releases a tremendous amount of energy in the form of radiation, which in turn creates a powerful outward pressure. This pressure should, in theory, act as a natural regulator, pushing away incoming material and preventing the black hole from feeding too quickly. This creates a natural growth speed limit, a physical barrier known as the Eddington limit. Yet, these ancient black holes appear to have violated this fundamental constraint with impunity, as if the law did not apply to them. We observe absolutely nothing comparable to these little red dots in the nearby modern universe. They appear to represent a completely extinct class of cosmic objects that thrived only during the universe's most chaotic earliest epochs. Their disappearance raises profound questions about what catastrophic events ended their reign. The sheer number of them, turning up in every deep image Webb takes, suggests they were not a rare phenomenon, but common and perhaps essential features of the primordial cosmos. Their abundance implies that supermassive black holes played a dominant and perhaps even a primary role in the formation of the first galaxies. This forces a complete reversal of our thinking. We had long assumed that galaxies formed first, and the black holes at their centers grew slowly within them over billions of years. But what if the black holes came first? What if these supermassive objects acted as the gravitational anchors, the cosmic seeds around which the first galaxies rapidly and violently formed? The plot thickened dramatically when a team of astronomers at the University of Missouri stared at their freshly processed computer screens in utter disbelief. 300 distinct objects blazed across Webb's infrared images with an impossible, searing brightness. These cosmic ghosts appeared in the deep past, where, according to our models, nothing of that luminosity should exist, challenging our most fundamental assumptions about the early universe. Hao Jingyan, the lead researcher on the study, cautiously describes these mysterious objects as candidate galaxies from the universe's infancy. The qualifier candidate reflects the team's profound uncertainty about what they had actually discovered. These objects shine far, far brighter than any model predicts early galaxies should be capable of achieving. Their brightness measurements tell a deeply disturbing story. These objects are emitting light equivalent to mature galaxies containing hundreds of billions of stars. Yet they existed when the universe was barely 5% of its current age. The cosmic timeline simply does not allow for such massive stellar populations to form and mature so quickly. Standard cosmology predicts that early galaxies should appear faint and small, their light stretched and dimmed by its journey across billions of years of expanding space. They should register as barely detectable whispers from the cosmic past. Instead, these 300 objects are screaming across space with a bewildering, impossible intensity. The statistical odds of such a discovery occurring by chance, if our models are correct, approach zero. Something fundamental is desperately wrong with our cosmic models. In a galaxy named GNZ11, a previously known contender for the most distant galaxy, Webb found something truly impossible lurking at its cosmic center, a supermassive black hole weighing 1.6 million times more than our Sun. This monster existed when the universe was only 400 million years old, far, far too early for such giants to exist according to our theories of growth. This landmark discovery came from combining Webb's unparalleled infrared vision with the Chandra X-ray Observatory's penetrating gaze. The black hole announces its presence through the high-energy X-ray emissions generated by matter being heated to millions of degrees as it's devoured. The existence of this monster so early on solidifies the paradox. The mathematics simply does not work within the confines of known physics for a black hole to grow this big, this fast. Roberto Maiolino from the University of Cambridge led the team that confirmed its existence. Their spectroscopic analysis revealed extremely dense gas moving at thousands of miles per second around the galactic core, velocities that require a gravitational field so intense that only a supermassive black hole could possibly generate it. This finding is a powerful piece of evidence suggesting that supermassive black holes may have emerged first, acting as the gravitational anchors that shaped and accelerated galactic evolution from the very beginning. The crises continue to mount, extending beyond gravity and structure into the very chemistry of the early cosmos. Oxygen atoms, forged in the hearts of stars, are floating through the ancient galaxy, JWST 490, in quantities that simply should not exist. This simple chemical element tells a complex story of impossible stellar evolution, occurring when the universe was barely 300 million years old. The presence of significant amounts of oxygen this early in cosmic history breaks the fundamental rules of nucleosynthesis. Oxygen creation requires a full, complex stellar life cycle that should take hundreds of millions of years to complete. Massive stars must first ignite, burn through their hydrogen and helium fuel, and then explode as supernovae. Only during these catastrophic explosions do their stellar cores forge oxygen atoms and scatter them into the void. Then, a second generation of stars must incorporate these newly available heavy elements into their own formation process. Jacob Helton, the lead researcher studying the chemistry of this ancient galaxy, describes the discovery of substantial oxygen as genuinely shocking. The measurements indicate that the galaxy had already been forming stars for potentially 100 million years before the moment Webb observed it. This pushes the dawn of star formation back to within 200 million years of the Big Bang itself. If this galaxy contains significant oxygen, it must have already completed multiple generations of stellar evolution. First-generation stars needed time to form, live their entire, brief lives, and explode. Then, second-generation stars had to form from the oxygen-enriched gas clouds left behind by those explosions. This finding has profound implications for the search for life in the cosmos. If heavy elements, the building blocks of planets and biology, appeared much earlier than expected, then rocky, potentially habitable worlds could have formed billions of years sooner than we previously imagined. Then, there is the universe's expansion. It is expanding, but scientists cannot agree on how fast. This nagging disagreement, known as the Hubble tension, represents one of the most significant and persistent crises in modern cosmology. Two different and highly respected measurement methods produce conflicting results that refuse to reconcile, despite decades of increasingly precise observations. The first method, championed by Nobel laureate Adam Rees, measures the expansion rate today by using nearby pulsating stars called Cepheid variables as standard candles. This method consistently yields a faster expansion rate of 74 kilometers per second per megaparsec. The second method looks back in time, examining the cosmic microwave background, the faint afterglow radiation from the Big Bang itself. These primordial measurements, captured with exquisite precision by the Planck satellite, predict a slower expansion rate for the modern universe of only 67. The 7-unit difference may seem small, but it represents a profound, unbridgeable disagreement about the fundamental nature of cosmic evolution, and it far exceeds all known sources of measurement error. The great hope was that Webb's involvement, with its superior clarity and precision, would finally resolve this cosmic mystery. Its unprecedented infrared sensitivity allows it to observe Cepheid variables with far greater accuracy than Hubble, eliminating potential errors from dust and stellar crowding. Instead of solving the problem, Webb hammered the final nail in the coffin of that hope. With even greater precision, it confirmed the higher, faster expansion rate of the local universe. The tension is real, and it is not going away. This confirmation eliminates the comforting possibility that observational mistakes explain the disagreement. Something much more fundamental, and likely much stranger, must account for the conflicting measurements. Either unknown physics is governing the expansion of the universe, or our models of the early universe contain serious, catastrophic flaws. In the primordial universe, stellar nurseries were operating at impossible, frantic speeds. Vast clouds of gas that should have taken hundreds of millions of years to slowly cool and collapse into stars were somehow completing this entire process in cosmic eye blinks. Webb is revealing galaxies containing billions of stars that formed when the universe barely had time to cool from the Big Bang's initial searing heat. Modern star formation follows predictable, well-understood patterns that require 50 to 100 million years from the initial collapse of a gas cloud to the ignition of a star. The early universe, with its higher ambient temperatures and lack of heavy elements to act as coolants, should have made this process even more difficult and much, much slower. Yet, Webb observes ancient galaxies that achieved star formation rates thousands of times higher than the most active star-forming regions, like the Orion Nebula in today's universe. One possible explanation involves the absence of stellar feedback in these primordial galaxies. In modern galaxies, star formation is a self-regulating process. The explosions of the first massive supernova and powerful stellar winds from young stars inject huge amounts of energy and momentum into the surrounding gas, heating it up and halting any further collapse. But perhaps early galaxies avoided these disruptions for a critical period, allowing an entire galaxy's worth of pristine gas to collapse all at once, triggering unimaginably explosive star formation episodes that consumed vast quantities of material in cosmically brief periods. Then there is the confounding problem of cosmic dust. These microscopic solid particles, the silicates and carbon compounds that are the essential building blocks for planets like Earth, should not exist in any significant quantity so early in cosmic time. Dust is primarily formed in the cooling outer atmospheres of dying stars, like red giants. This is a process that requires stars to have already evolved through their complete life cycles. Yet, Webb is observing the unmistakable chemical signatures of dust grains and galaxies that existed when the universe was barely 500 million years old. These ancient dust grains appear, chemically, to be indistinguishable from the particles found in modern galaxies. The cosmic timeline simply allows insufficient time for these traditional dust production pathways to operate. Hiroshi Nagai, a researcher leading the study of early universe dust with Webb, has now identified dust signatures in dozens of ancient galaxies, confirming that particle production began almost immediately after the first stars ignited. This early dust problem connects intimately to Webb's other discoveries. If dust formed faster than expected, it might provide the very cooling mechanism needed to explain the rapid star formation rates, as dust grains are excellent radiators of heat. But this simply pushes the problem back one step. Where did the impossibly early dust come from? It's a cosmic chicken and egg problem of the highest order. In the cosmic dawn, Webb also discovered sleeping giants where none should exist. These are dormant, or quenched, galaxies containing billions of stars, but showing no signs of active star formation. Despite existing when the universe was less than 1 billion years old, their peaceful slumber defies every model of early galactic evolution. Astronomers have nicknamed them Sleeping Beauty galaxies. These are massive structures that somehow manage to race through their entire star-forming life and exhaust their fuel, entering a state of cosmic hibernation. In the modern universe, such dormant systems are common. They are the end state of galactic evolution. But finding them in the early cosmos is a fundamental violation of our established cosmic evolution timelines. Kate Whitaker, from the University of Massachusetts, leads the research into these enigmatic systems. Her team has identified 12 of these dormant galaxies in regions of space where frantic, active star formation should be the dominant activity. These objects appear fully mature, old, and settled, despite existing when the universe itself was still in its chaotic, violent infancy. They somehow transitioned from a state of active star formation to complete dormancy within just a few 100 million years of their birth, achieving a mature status faster than physics should allow, and then abruptly ceasing all stellar production. Across Webb's infrared vision, an impossible and spectacular collision unfolds. 5 separate galaxies are caught in the act of spiraling toward mutual destruction, locked in a cosmic dance that, according to statistical models, should occur perhaps once in the entire observable universe over its lifetime. This exceptionally rare merger system, nicknamed the quintet, defies the statistical laws that govern galactic encounters. Wider from Texas A&M University leads the team studying this unprecedented cosmic catastrophe. The probability of detecting even one 5-galaxy merger is vanishingly small. To find such a system so early in Webb's observational mission suggests either a case of extraordinary, lottery-winning luck, or more likely, a fundamentally flawed understanding of the conditions and dynamics of the early universe. This spectacular merger is happening as it appeared 800 million years after the Big Bang, a time when galaxies were more densely packed, but still separated by millions of light-years of space. Orchestrating a 5-way collision requires a precise, near-perfect alignment of trajectories across vast cosmic distances that simply staggers the imagination. This discovery raises profound questions about the prevalence of such massive mergers in the early universe. If 5 galaxy collisions were, in fact, common, they might help to explain some of Webb's other puzzling observations, including the formation of the oversized ancient galaxies and the fuel sources for rapid black hole growth. Every single one of these predictions made by the standard model of cosmology now lies in ruins around the observational data from the James Webb Space Telescope. The Lambda CDM framework, the elegant theory that has guided astronomical research for 3 decades, cannot explain the telescope's most basic, foundational discoveries. Galaxies appear where none should exist. Black holes grow faster than physics allows. The universe expands at contradictory rates that violate our theoretical constraints. The cosmological crisis, which began with Webb's very first scientific observations, has only deepened and broadened with every subsequent data release. Galaxy formation timelines have been proven completely wrong. Star formation rates have exceeded all theoretical limits. Chemical evolution has proceeded faster than the laws of nuclear physics permit. Each new discovery has demolished yet another pillar supporting the edifice of modern cosmological theory. Dr. Sarah Rodriguez leads an international team of theorists who are attempting to salvage the Lambda CDM model through increasingly desperate and complex modifications. But none of their proposed theoretical patches have succeeded in addressing more than a small fraction of the accumulated, contradictory problems. The failure is so comprehensive, so fundamental, that it forces us to confront an uncomfortable and profound possibility. The universe may operate according to principles that remain completely unknown to modern science. Webb may be revealing a cosmos that is governed by an entirely alien set of physical laws. Theoretical physicists are now scrambling to invent new mathematics, new concepts, capable of describing Webb's impossible observations. The required modifications span every single branch of physics, from the quantum mechanics that governs the very small to the general relativity that governs the very large. No existing theory seems to survive contact with Webb's observational reality. The list of theoretical innovations now being seriously considered to explain Webb's discoveries includes modified gravity theories, where gravity is stronger on large scales, exotic dark matter interactions, the idea that fundamental constants of nature are not constant at all, the existence of primordial magnetic fields, and entirely new classes of particles never before imagined. The most terrifying possibility emerging from Webb's cosmological crisis is that the laws of physics themselves appear to change across cosmic time. The strength of gravity, the speed of light, the masses of elementary particles, these values we consider immutable, might fluctuate according to unknown principles that would render the universe an inherently unstable construct. If these fundamental constants have evolved, then nothing about physical reality can be considered permanent or reliable. The universe would operate as a dynamic, shifting system, where even basic mathematical relationships change over time. Dr. Paul Davies, a renowned theoretical physicist, leads research into these variable constant theories. His analysis suggests that the gravitational constant might have been significantly larger during the universe's first billion years, allowing for the kind of rapid structure formation that is impossible under modern physics. Evidence for this radical idea is emerging from the detailed analysis of the stars in Webb's most distant observations. They appear to be burning through their nuclear fuel at rates that exceed our theoretical predictions by factors of 10 or more. This incredible acceleration could be the result of stronger gravitational fields compressing their stellar cores more efficiently. Initial, tentative results from Webb's data already suggest subtle but significant variations in several of these fundamental parameters. The electromagnetic fine structure constant, which governs all of chemistry and light, appears to be roughly 1% different in galaxies observed at a redshift of 10 compared to its modern terrestrial value. This tiny change, if confirmed, would have profound and cascading consequences for all of cosmic evolution. At the smallest, most fundamental scales of space and time, our reality dissolves into a seething, chaotic quantum foam, where virtual particles constantly pop into and out of existence. Webb's observations are now suggesting that this microscopic chaos might be the very thing that governs cosmic evolution on the largest of scales, revealing the universe as a fundamentally unstable construct, balanced precariously on the edge of non-existence. The research of physicists like Dr. Michio Kaku into how quantum foam might influence cosmic structure suggests that quantum fluctuations in the early universe could have generated matter distributions that are impossible under classical physics, thus explaining Webb's observations of impossibly early galaxy formation. This quantum foundation might be the reason why Webb observes galaxies that violate all of our classical physics predictions. If space-time geometry itself fluctuated wildly during the cosmic dawn, our normal understanding of gravitational physics would not apply. Matter could have concentrated into galactic structures through bizarre quantum tunneling effects rather than the slow, gradual process of gravitational collapse. Across billions of light years, filaments of dark matter are now known to weave a cosmic web that connects every galaxy in patterns that are too organized to result from random gravitational forces alone. James Webb is revealing that this largest of all structures in the universe appears to be designed according to principles that suggest an intelligence, or at least an organizing principle, operating on scales that dwarf human comprehension. Computer simulations can reproduce the filamentary structure, but they fail to explain the precise, almost geometric, mathematical relationships that govern the web's intersections, lengths, and connectivity patterns. Professor Joel Primack from the University of California has found that the cosmic web's architecture seems to follow optimization principles that would minimize the information transfer time between widely separated regions of space. The dark matter filaments appear almost as if they were designed to facilitate rapid, efficient communication. This suggests that the requirements of information flow, not just gravity, may have shaped the evolution of cosmic structure. The universe, in this view, might function as a vast information processing system. Webb's detailed observations are revealing smaller-scale structures within the cosmic web filaments that bear an eerie resemblance to biological neural networks. This forces us to confront the most speculative and perhaps most profound possibility of all, that intelligence is not a small, localized phenomenon, but a fundamental property of the cosmos itself. Every single assumption that has defined human understanding of reality is now crumbling beneath the sheer weight of the James Webb Space Telescope's revelations. We inhabit a cosmos that follows no rules comprehensible to terrestrial intelligence. The scientific method itself becomes questionable when applied to phenomena where the act of observation changes the observed, and the act of measurement creates the measured. The collapse of certainty extends beyond astronomy to every branch of human knowledge. Dr. Maria Santos reports widespread existential depression among her astronomer colleagues, who are being forced to confront the utterly alien nature of cosmic reality. Webb forces humanity to acknowledge its cosmic insignificance, not merely in terms of our physical scale, but in terms of our comprehension. We inhabit a cosmos that operates according to principles that may transcend our very cognitive architecture. In the darkness between the stars, the questions are now multiplying like a cosmic cancer, eating away at every assumption humanity has ever made about existence. James Webb has opened doors that can never again be closed, revealing mysteries that will torment human consciousness until the last star burns out. What intelligence designed the perfect geometry of the cosmic web? Why do the fundamental constants of nature appear to change across cosmic time? How do galaxies form before the universe itself allows for their existence? We have seen too deeply into the cosmic mystery to ever again mistake our human knowledge for universal understanding. James Webb looked too deep into space and found that space is looking back with an intelligence or an organizing principle that makes human awareness seem like a mere quantum fluctuation in an infinite ocean of consciousness. And the final, most haunting question of all remains: what will we discover next?